In this video, we're going to discuss derivatives of maps between Banach spaces, and in particular, we're going to state and prove the chain rule. Now, when we think of functions of a single variable, so when we talk about differentiability in elementary calculus, so we start with a function f that goes, for example, from an interval ab to the real set R, and we think of a derivative as a function f prime that goes from the same interval AB to R. Now, when we talk about the Banach spaces, this concept is going to be different because for Banach spaces, when we think about differentiability, then this means that there exists a linear map between, so from one Banach space, the linear map that maps one Banach space into the other one. And this linear map represents an approximation of the function near a point x, a linear approximation. So let's start with this definition. So we say that, so let's consider, first of all, two Banach spaces x and y. So x and y are Banach spaces. I recall Banach spaces means complete metric spaces. It means every Cauchy sequence is going to be convergent in those spaces. So x and y are Banach spaces. Let's consider a function f that is defined on a subset of x. Let's call this a subset, open subset of xu. So it's mapping to y. And we say that f is differentiable at a point x that belongs to u if there exists a linear map A from x to y such that if we take the limit for h that goes to 0 of the norm of the function f of x plus h minus f of x minus a times h, and then divide by the norm of h, then this quantity is going to be equal to 0. So for this limit to go to 0, this means that the numerator needs to go to 0 faster than the denominator as h approaches 0. And therefore, we can use an alternative definition in terms of a small o notation. And in order to understand what this means, we are going to define a function, let's say r, from u of x into y. And we say that r of h is equal to small o of h if the limit for h that goes to 0 of the norm of RH divided by the norm of h is equal to 0. So this means that the numerator is going to go to 0 faster than the denominator as h goes to 0. So we can now redefine the concept of differentiability using the small o notation. In fact, this definition is equivalent of saying that f of x plus h can be written as f of x minus, well, plus a times h, and then plus this term we're going to call r of h. Well, r of h is equal to small o of h, because if you isolate from here r of h, what we get? Well, let's do it. If we isolate r of h, we get f of x plus h minus f of x minus ah. So r of h is equal to this term here at the numerator. And since r of h is going to be equal to small o of h, by definition, the limit for h goes to 0, r of h divided by the norm of h needs to be equal to 0. So it's just a different way to define the concept of differentiability, but it will be very useful in proving the chain rule. Okay, so now we're going to prove the chain rule. We're going to state first this theorem and prove it. So suppose that we have three Banach spaces, x, y, and z. And let's assume also we have this function f, which is differentiable at the point x, defined from u of x to y. And let's say that f is differentiable at x that belongs to u. And then g, which is defined from an open set v of y to z. And let's assume that g is differentiable at f of x that belongs to v. Then the theorem states, so under this assumption, we have that g composite f is differentiable at x, and if we take the derivative of g composite f prime, this is equal to, so at point x, this is going to be equal to g prime evaluated at f of x times f prime of x. Okay? Now, remember we said a function is differentiable if there exists this linear map. We call this linear map A from x to y, and such that the limit for h equals to 0 of the quantity we wrote previously is equal to 0. Now, this map A is usually written also as f prime of x, which indicate, this concept of derivative of x. So usually this map A is denoted by f prime of x. So we're going to use this notation. Okay, so we know that f is differentiable at x that belongs to u. So by differentiability of f, so here I'm writing the proof. So by differentiability of f, then we can write that f of x plus h is equal to f of x plus, remember it was a times h, but now instead of a I'm going to use f prime of x times h, and then we add that small o of h, so which we call r of h, right? Remember r of h means that the norm of r of h is going to go to 0 faster than the norm of h as h approaches 0. Also, now we're going to use the concept of differentiability of g, but before we do that, let's make a substitution. So let's substitute y with, so f of x with y, and let's call this term here as a k. So k will be equal to f prime of x times h plus r of h. Okay? Alright, so by differentiability of g, we can write that g of y plus k, where y is f of x, well, is equal to what? Well, let's use this expression. So g, similarly, we have g of y, so g of y plus g prime evaluated at y times k in this case, not h but k, plus let's call this s of k, which is a small o of k, means again that the norm of s of k is going to go to 0 faster than the norm of k. Alright, so at this point, we can rewrite this g of y plus k as what? Well, g of y plus k is the same. What's y plus k? Remember that y is f of x, so this is y, plus, and this term was k. So y plus k is the same of f of x plus h. So now I can write that g of f of x plus h is equal to what? Well, this is equal to g of y, which I'm going to keep, or I can write the g of f of x, which is the same, plus, actually, let's do that. So instead of g of y, let's write g of f of x. And then we have a plus g prime of y that multiplies k. But k is what? Is f prime of x times h, and then we have plus g prime of y, so I'm just using distributive property here, times r of h plus s of k. Alright, so at this point I'm going to rename this last piece on the right hand side, so all of this, with t of h. So t is a function of h. And in order to prove this theorem, the only thing we need to do is prove that the limit for h that goes to 0 of the norm of t of h divided by the norm of h must be equal to 0. Okay, so we want to prove practically that t of h is equal to small o of h. And this will prove that the g of f of x is differentiable at the point x, and that the derivative is equal to g prime of f of x, because this y, remember, is f of x here, right? Times f of prime of x, okay, because that's a derivative. Okay, so to prove that, let me erase this part. So we want to prove that the limit for h equals to 0 of t normative h divided by h is equal to 0. Well, let's do a substitution. What's this limit equal to? Okay, so we have the limit for h that goes to 0 of the norm of t of h divided by the norm of h is equal to the limit for h that goes to 0 of this quantity, which is the norm, of g prime of y r of h plus s of k. And then everything divided by h. Okay? Alright, so at this point we are going to use the fact that the norm of a product is less than or equal to the product of the norms. So we have a limit h goes to 0 of the product of g prime of y times the norm of times yes, so let's see, let me write this. So g prime of y times the norm of r of h divided by the norm of h, and then we have plus the norm of s of k, and then divide by h. So I'm going to put h here for right now, the norm of h. And now what we're going to do here is multiply and divide by the norm of k. But the norm of k, so I'm going to write the norm of k here, and here at the top of the numerator I'm going to put the norm of g prime of y times the norm of RH, and then plus, so k was, no, sorry, k is, so only need to put k. So the norm of k is this one. So the norm of this quantity, which is f prime. So I'm going to use still the fact that the norm of f prime of x times h is less than or equal to the norm of f prime times the norm of h, and then we have a plus r of h, and this needs to be norm. Okay, hopefully you can see that. All right, and then what we have is that since g is differentiable at y, which is because y is f of x, then this quantity we know for sure that it's bounded. So this quantity is less than infinity. It's going to be a bounded quantity. And we also know that the limit for h that goes to 0, this quantity is going to be equal to 0. So all of this is going to go to 0. Alright, so in here what we have is that the norm of our h divided by h is going to go to 0. If we break this down, this fraction, and then here we have the norm of f prime times the norm of h over h and h is simplified. So all of these practically is going to simplify to the norm of f prime, right? And then here we're left with the norm of sk divided by k. Okay, now as h goes to 0, this quantity for prime of x times h plus r of h is going to go to 0. But since sk is small o of k by the differentiability of g, this is o of k, then this limit is going to go to 0 faster than k approaches 0. So this quantity is also going to go to 0 as h approaches 0. And therefore, this limit is equal to 0, which is exactly what we want to prove, which implies that t of h is small o of h, and therefore the derivative of g composite f is differentiable, and the derivative is equal to g prime of y f prime of x, which is also g prime of f of x multiplied by f prime of x.